just visually what's going on. See, here we've got sort of the same concentrations we did before, and we take the N2 going up from 0.5 to 1.5, and at that point, what would happen is we'd have a reaction moving in the forward concentration. The amount of N2 would go down. It wouldn't go down to what it was beforehand. The amount of ammonia goes up, the amount of H2 goes down. It's decreasing at a rate of 3 times the rate that nitrogen's increasing. And so it's at equilibrium before, we add N2, that changes the equilibrium. We still have more N2 than we did before we added N2, but it goes down from the amount we added in order to reestablish the equilibrium. Right. So at this point, QC is equal to KC, and at this point, QC is equal to KC as well. And until it reaches equilibrium, then QC is less than KC. So that's the use of the equilibrium quotient. It helps us understand exactly what's going on in the system. Okay. So one thing to think about, this is an elaboration question. How can I make this question different while testing the same concepts? What other things could I do? I could, add a different compound. I could add more of the compound. I could subtract some of the various compounds. So think about that. So when you're doing these problems, keep asking yourself questions like that. And if you can solve those alternate questions, or you can figure out how to solve them based on the questions that are being answered, you're in good shape. Okay. So calculating equilibrium concentrations, that is a qualitative thing to do, but we can make this quantitative as well. Okay, so let's say we have a reaction, a hydrogen and fluorine are reacting to make hydrofluoric acid, and the Kc I'm giving you here is 115. Okay. We place 3.000 moles each of H2 and F2 gas and 1.5 moles of HF gas in a 1.5 liter flask. What are the concentrations at equilibrium if the temperature is held constant? Okay, so we have enough information here to solve it. Let's start writing an equation. We've got an inequality. Let's write an equation. And really, although there's 3 concentrations, there's only one variable. How far has the reaction gone? Because the changes in all of these species are related. So there's one constraint, here's the equilibrium constant, and there's one variable, how far has the reaction proceeded? So let's try to write out the equation. So we have, shift to edit mode, we have that Kc is equal to HF squared over H squared F, H2F2, neither of those are squared, equals 115. But I still have 3 variables. How do I write this in a way that's simply one variable? And a simple way to do this is something called, a good way to keep track of all of this is an ICE table. You may or may not have seen this, but the basic idea is ICE is initial, that's the I, change, that's the C, and equilibrium. That's the E. All right. So we have a table, and the columns of the table are our species, H2 that are involved in the reaction, H2, F2, and HF. And then we have 3 rows, ICE, for the initial, the change, and the equilibrium. So the initial, well, the initial concentration of each of these is 3.0 divided by 1.5 equals 2.0. We know it's 3 significant, they've got 4 significant digits, but we'll just write them with less and then we'll report the answer because these are very precise because the numbers, you can just write 2 and we know that there's 4 significant digits. We'll remember that at the end. So the concentration is 2.0 here, 2.0 here, and the initial concentration of HF is just 1 molar. So that's 1 molar. So those are the initial concentrations. The change, well, however much of hydrogen reacts, we'll call that X. We know that F2, because of stoichiometry, reacts exactly by the same amount. And then finally, we know that the amount of hydrogen fluoride that's formed is for each molecule of H2 that disappears, we can get a 2x, we get 2x molecules of HF. So then at equilibrium, what we have is the initial plus the change. So this would be 2 minus x here, 2 minus x here, and 1 plus 2x. So now we can fill this in. 1 plus 2x squared divided by 2 minus x times 2 minus x. And that is equal to 115. So we have an equation for, we have one equation and one variable. So we should be able to solve this. Now the question is, what kind of equation is this? And the answer, looking at it, well, I'm squaring x. It looks like it is a quadratic equation, and that's exactly what it is. In these equilibrium problems, you frequently have quadratic equations. So there's a faster way to solve this particular problem, but it doesn't always work. So let's focus on the general way, and then I'll come and show you a quicker way for this one. So multiplying this out, we get 1 plus 4x plus 4x squared. And then on the bottom, that's 4 minus 4x plus x squared equals 115. Then we can multiply both sides by the denominator of the left side, and we get 460 minus 460x plus 115x squared is equal to 1 plus 4x plus 4x squared. And so that gives us in the end, once we collect terms, 111x squared minus 464x plus 459 equals 0. And we can then plug this into the quadratic equation, right? The quadratic equation is x equals minus b plus or minus b squared minus 4ac all over 2a. Where this is a equals 111, b equals minus 464, and c equals 459. Now, at this point, it's just plugging it in. There'll be two answers. Whenever you have a quadratic equation, there's two answers. And what you'll find in these equilibrium problems, only one of the answers is physical, and we'll see. So I will not plug this in. I'll not do all the calculations right here. You can plug it into a calculator. What we get out is this is equal to 1.607 and 2.573. So which of these could be right? Well, the thing we usually want to do is check. A common problem, one of the most common problems with the wrong answer is it makes a negative concentration. So we can see here that one of the final equilibrium numbers is 2 minus x. Well, 2.573 is bigger than 2. So therefore, that would lead to a negative concentration of hydrogen. In theory, that would satisfy this equation, but it's physically meaningless. So this is not the answer. So once we have that, we can just plug everything in. So that would leave a concentration of hydrogen, and that's equal to the concentration of fluorine gas. 2 minus 1.607 equals 0.393, and HF is equal to 1 plus 2x, which ends up being 4.21. So we can plug this in to verify, right? That you always want to plug something in to make sure you're right. So in this case, it would be 4.21 squared over, well, these are all 0.393 is what they both are. Square that. And when you multiply that all out, you find that it is indeed equal to, up to rounding errors, 115. So this satisfies the equation. So this is a way we can solve these sorts of equations. We always have a way to solve these sorts of equilibrium equations. We plug in, there's going to be one variable, the extent to which the reaction has occurred, and we plug it in, we get a quadratic equation, and we solve the quadratic equation. We figure out which answer is non-physical, eliminate that, and then just plug that in. Remember, the x is not the answer, the x is the change, and so we need to plug the change in to get what the final concentrations are. One other thing to think about, I wrote it as minus x here. But how did I know that x is disappearing? Could have used plus x? Yes, and what you would have gotten at the end is you would have gotten that x equals minus 1.607 and minus 2.573, which is physically exactly the same thing. Could you have used X as the amount of HF coming up? Yep. And what you would have got an answer that was twice as big. The hydrogen Fs would have been changing by -1/2 X, and you would have gotten the exact same physical same thing. So it doesn't really matter what you choose as the thing that is changing. They will all give you the same physical answer, the same concentrations in the end. Okay, so let's I'll show one thing. Let me show you like a fast way to do this particular one. But I don't know that it's sort of cute that you can do some problems like this. So I've got the ice table pre-written out, right? I have Kc again is 1.2x, 1 plus 2x squared over. Now notice it's 2 minus x times 2 minus x, which is just 2 minus x squared, which gives 115. So what I could do is just take the square root of both sides. And what I get is 1 plus 2x over 2 minus x is equal to plus or minus, we're taking a square root, 10.724. And then I have two equations that I have to solve. One is this one, 1 plus 2x divided by 2 minus x equals 10.724. And on this side of 1 plus 2x divided by 2 minus x equals minus 10.724. This one, you multiply both sides by 2 minus x. You end up getting 1 plus 2x equals 21.448 minus 10.724x, which when you collect terms, gives you 12.724x equals 20.448, and x equals, this is going to look familiar, 1.607. And on this side, 1 plus 2x equals minus 21.448 plus 10.724x. This leads when you simplify everything out, minus 8.724. X equals minus 22.448, or x equals, totally unsurprisingly, 2.573, which are the exact same answers that we got on the previous page. Right, there we go, 1.607, 2.573. So this, sometimes you can find quicker ways to do problems. My personal feeling is that usually you're better just using the quadratic equation, getting used to that, because that always works. That is the way that gives you the answers to a quadratic equation. So there's a slick way here, quadratic equation. When we look at acids and bases, in the book it goes over various rules. When we look at acids and bases, some of those rules end up, like simplifying rules, end up applying like 99% of the time. So they're useful in looking at. But in general, I think the quadratic equation is a little bit safer, a little bit more direct if you can manage to plow through the algebra. But nowadays there's computer programs that can help you plow through the algebra to solve it. So on the exam, if you write down the quadratic equation, identify what A, B, and C are, and then saying I'm plugging this into the equation using some calculator, that's fine as long as you can write out the proper quadratic equation.